is my slides ready? Oh, all right, thank you. So today I'm going to talk about ZJIT, which is the next generation of the JIT compiler we have in Ruby 3.4 as YJIT. So, and also the future of that next version. So my name is Takashi Kokubun. I'm on the Ruby JIT team at Shopify for like 3 years now. And I'm also been Ruby committer for 8 years, working mostly on Ruby JITs. So like there have been 4 different Ruby JITs merged to C Ruby. They are MJ, RJ, YJ, ZJ, and I've contributed to all of them. So yeah, like worked on a lot of Ruby JIT stuff. And we have YJIT and ZJIT in the current Ruby master. So I'm going to talk about 2 of these today. So the first one, YJIT, is the Ruby JIT that was merged to Ruby 3.1. You can use it by passing --YJIT because by default it's not enabled. So if you need to run a script with YJIT, you need to use the --YJIT option. It's a production-ready JIT compiler. We use that as Shopify for tier 1 services and get a speed up as well. And many other companies, we have so many reports that many other companies use that in production as well, and also got a speed up like 10 or 20%. And thankfully, Rails 7.2 added a feature to enable YJIT by default in the initializers. So even if you don't realize, you may already be using YJIT in production if you already use new enough Ruby and Rails. So here's the Ruby bench suite comparison between the interpreter and the YJIT. So this benchmark suite is called Ruby Bench now, but it's formerly called YJIT Bench. It's transferred to Ruby organization now, and we have a lot of so-called like real-world benchmarks like Rails Bench and other Rails applications such as Lobsters, which is a Hacker News like website, and also we have ShipIt, which is another Rails application on Shopify. So we can see that on such Rails application benchmarks, we can see some speedups. Like for example, the Rails bench is a scaffold and active record query and kind of very full stack, but still simple Rails application. But we get twice as fast as the interpreter. So it doesn't directly translate to the production performance, but we still get the nice speed up in production as well. So this is the Shopify storefront vendor service that has a lot of traffic, and like it's actually the service that gets the largest traffic at Shopify. And we see this kind of speed up in production, like 10% to 20% on average. So ZJIT is the version that we are currently developing. So if you haven't realized yet, the next Ruby version is now called Ruby 4.0. That was formerly developed as Ruby 3.5, but Matt announced this month that we were going to be calling it Ruby 4.0. So, and ZJIT is the next JIT compiler we are developing this year and merging to Ruby 4.0 for the first time. So YJIT this year didn't get much optimization. If you go back to the comparison between Ruby 3.4 and 4.0, that's not much difference because we didn't add any optimization features. But this year, we were mostly focusing on developing this new JIT compiler, ZJIT. Unfortunately, this is still experimental, and we are not expecting people to evaluate that just yet. We are hoping to make it more productionized and faster at Ruby 4.1. But to get started on developing a new version, we already merged that to Ruby 4.0, so you can kind of use it. We don't recommend enabling that in production just yet. We still ask you to use YJIT at Ruby 4.0, and we also don't just expect speed up from upgrading Ruby 3.4 to 4.0, but it is what it is. And the reason why we are investing so much in ZJIT by like not giving a speedup this year, but also just making a yet another JIT compiler at Shopify is that in YJ we weren't able to do some kind of optimizations, which is cross-instruction optimizations. And at YJIT we had some block local. So like if you have a Ruby code that's spread into multiple basic blocks, and then basic blocks are just a block that doesn't have a branch, and those basic blocks are optimized one by one, and we don't necessarily be able to can't optimize that across different basic blocks with the YJIT design easily. Or if we need to do that kind of thing, we need to use more memory to allow the cross-block optimization, like remembering the context of the block at the end and then passing it to the other block allows you to optimize that. But as a production user of Ruby JIT, we were sort of, we cared about the memory usage of YJIT, so we weren't able to comfortably keep adding the new optimization that would require more use of memory. So we wanted something that where we don't need to care about, we don't need to worry about the increased memory usage for adding new optimizations. So we kind of changed the design to make it easier, basically. So here's how YJIT works. This is an example Ruby code, and in the interpreter, we compile that into so-called bytecode. That's the Ruby virtual machine interprets this virtual machine code, and this is very specific to Ruby virtual machine. And the interpreter interprets it by one, and then YJIT starts generating the machine code for this bytecode, translating each bytecode one by one. And then what YJIT does is to profile the types at the runtime, we need to split the block into like smaller pieces than the actual basic blocks, such as this get_const is referring to the constant 2. And to get the type of constant 2, if you just look at the bytecode, you just know the name of the constant, that is 2, but you don't know what is inside. So to inspect the type of the instruction used by the instruction, we kind of had to split the basic blocks, and then also remember a lot of stuff in the so-called context metadata. So we just store anything that's useful for optimization in the context metadata that consumes memory, and then also split a lot of blocks for profiling purposes. So like, because we compile one block at a time, if you carry on those contexts, first of all, that consume memory, and also we can't easily compile different blocks at the same time. So, which is why the first block writes 1, and then second block writes 2, and then the third block finally adds that 1 and 2, and then return that. But if you look at this Ruby code, you might want to just return 3 as long as the constant has not been redefined. So that's what we kind of want to do with ZJIT. So here's how ZJIT works. So to profile the types got by the instruction, we kind of use a different approach. So by doing the JIT code-based analysis, we were sort of forced to generate extra code and store memory. And so we kind of changed how we profile the runtime information. So we introduced a new instruction, like ZJIT underscore something for every instruction that we want to profile. So the bytecode that we want to profile will get this ZJIT underscore prefix when you reach certain threshold. And then once you execute this ZJIT underscore instruction for some periods of time, we get the profiling information, and then also start compiling the ZJIT the Ruby code into ZJIT's intermediate representation. Here we call it HIR, which is high-level intermediate representation. It's basically something we use for optimizing the Ruby language. So we now have 1 and 2, that the V1 and the V2 are that's not explicitly written, but this patch point thing, it's going to use V1 and V2. So it's not going to be written by the generated code, but the V3 has the value 3 that's added by the compiler. 1 plus 2 is already pre-computed at the compile time. And so the generated code will actually look like something like just return 3. So it's much faster with the patch point that will be invalidated when the const 2 is redefined or the integer path is redefined. So that's what we ideally want to do, and that's what we also do at ZJIT too. So I want to kind of talk about ZJIT IR. As I said, IR stands for intermediate representation. I think the core of ZJIT is that we now have the very Ruby language aware intermediate representation for optimizing Ruby. So if you have something like LLVM, that's an intermediate representation used by many other languages such as Rust or C or C++. That's useful, but if you just use that for CDB, what happens is when you look at the C extension function, for example, that has something like RB underscore funco, that's a method call into Ruby, but because the RB funco is implemented as like method dispatch, it needs to know the hash table it's prepared at the runtime to be able to know what's the jump destination of the call site of the RB funco. So LLVM cannot really figure out the target of the method call unless you populate all the runtime information into the LLVM IR. So it's not really easy for such language agnostic IR to optimize Ruby if you look at the CGB's context. So what we do with the ZJIT IR is we kind of provide a Ruby-specific IR that specializes into the CGB virtual machines context and do a very Ruby-specific optimizations. So that's what we are trying to do with ZJIT. We have two different IRs. One is called HIR, that just stands for high-level IR, and the other is called low-level IR. YJIT already had the same LIR that has just abstracting away x86 and ARM64, which are the two platforms we support. But YJIT didn't have the HIR one that now perform the language level optimizations. So this is just a Rust track that represents the HIR. You don't need to understand that, but just wanted to give an image of how that looks like. It has a bunch of struct that have something like instant ID. So in ZJIT HIR, we construct the IR in a way that it's so-called SSA, single static assignment. We assign a variable only once for each variable name. If we go back to HIR, there's V1, V2, V3 are sort of variable. Because we assign that only once, any reference to that variable can be replaced by the definition of that variable. So it makes it easy to optimize the IR. And because it's we basically rely on the optimization, we rely on the variable name to replace such operands. We call it instant ID instruction index as the variable name of the IR. So a lot of things have this instant ID, and we can replace it based on the property of the instruction. So like every such reference can be optimized by analyzing the IR. And we have a lot of optimization passes. So in compilers, like traditional compilers, like for example, LLVM, have a lot of so-called passes that are performed on top of the LLVM IR, and that does a transformation that's very general to the IR, but by combining those in order and multiple times, they can do a sophisticated optimization. And in ZJIT, we also do that kind of stuff by having these HR optimization passes. The first one is a type specialized, and because we have a type information provided by the ZJ underscore instructions, we populate the type information and replace, for example, the method call into the specialized method implementation, for example, just a C function call, or the definition of the method, such as if the one is just returned by the method, we just replace it with one. So that's what we kind of do for the problem that I just mentioned for the LLVM, which is RV function call cannot be easily optimized by the LLVM, but we can, with this Ruby-specific IR, we can do Ruby-specific and virtual machine-specific optimization, such as type specialization based on the ZJIT profiling information. And this inline pass, next inline pass is, we have some inlining optimizations. YJIT already also has some inlining optimizations, and we kind of copied it, but we plan on extending it more to more complicated methods inlinings. So more to come. We also have optimized get ibar, which is just get instance variable, and optimized C calls is just also optimization of the C calls. Fault constants is the most interesting one, I think, for ZJ. So the thing I showed earlier is just 1 plus 2. Computing multiple values at the compile time is something that YJIT wasn't able to do because of the restriction that blocks are often split, and we don't have enough context in a single block to optimize them together. But ZJIT, because it's a so-called method JIT that compiles the whole method at once, you know the whole context, whole graph of everything in the same method. And sometimes if you inline the method, you also have multiple graphs, the graph of multiple methods. So you can optimize a lot of things together. So by having this fold constants pass, fold constants means you have 1 and 2, for example, are the constants that are basically constants. That doesn't change. And because 1 and 2, the values given to the plus operation are constants, that can be folded into 3 at the compile time. So that's the fold constants pass 2. And creating CFG is just sort of refactoring of the IR. We just generate like smaller blocks, but then to eliminate jumps, we clean up the compiler control flow graph. And then we also eliminate the decode by analyzing the IR. So like because every reference is identified by the variable name, like V1, V2, V3. If now nobody references V1 and V2, for example, here the V2 and V1 and V2 are used by the patch point. But if there was no patch point for patch point 2 and integer plus, then nobody is going to reference the V1 and V2. So we're just going to drop the instruction from the IR. So nothing is going to be ever generated for such unused variables. So dead code animation is also kind of easy with the IR. Is not new, like it's just copied from YJIT, so nothing crazy, but it's just instruction that abstracts away the architecture differences across ARM64 and x86. So like, for example, the first instruction is just add, just adding left and right and inserting that into out, so very normal. We have some more passes than YJIT now. So the first pass is split, and we just split instructions into multiple instructions sometimes to allocate registers for instructions that cannot be encoded with the same operand as is. Sorry, it's a kind of minor detail, but then we allocate registers, which is a nice optimization, by the way. So when you are using the interpreter, what happens is every operand used by instruction is stored in the stack, which is memory. So like whenever you run the Ruby script with the interpreter, every time you execute the instruction, you read from memory and write into the memory. So it's kind of slower than using registers provided by the CPU. So by having this alloc reg, almost instantly gets you faster than the interpreter. And then compile exits is just compile code that's used by the patch points, and so-called side exits, that's for in case something happens, for example, like method is redefined or something like that, and scratch split is just a last minute split for encoding instructions, and then finally the emit pass that actually encodes the instruction into machine code. So this LIR is encoded into machine code by this compiler pass. So like a regular compiler pipeline, we now have two different IRs, high-level optimization passes, and then low-level passes. So like every optimization that was possible in the traditional compiler is now possible in the Ruby compiler as well. So if you have ideas that should be possible in the Ruby compiler, we can now do that in ZJIT. If you want to play with ZJIT, you need to, first of all, enable the ZJIT support. Currently, at the moment of the Ruby master, ZJIT support is not enabled by default. So when you configure Ruby, you need to --enable -ZJIT. And then once you build the Ruby with the ZJIT support, you also need to enable the ZJIT by -ZJIT. But if you want to play with the IR, for HIR, you need to use -ZJIT dump HIR. And for LIR, you have ZJIT dump LIR. And another interesting way to play with it is there's a website in the URL below called tryzjit fly dev, and that's an interactive HIR visualizer. There's a Ruby code shown on the left side, and then the right side shows the HIR for the Ruby code. I'm going to explain a little bit how this optimization works. So this is basically the same code as the previous slides showed. So as we said, we compile them into the bytecode, and then we also insert the profiling instruction. And then by profiling the type, so first of all, we compile the method code 3 into method code 1, method code 2, and then plus together. And because we had the profiling information, we can now inline the method code 1 and the method code 2 into something guarded by the method type, the receiver type check. The receiver type must be a top-level object. And then we also have a patch point that doesn't generate code, but that's there in case method is redefined or singleton class is created for the object. So no code, but basically type check. And then finally, we get constant folded value 3 and just return it. So yeah, this is how HR works. So I want to sort of touch on the future of Ruby performance. When we have this, when we are in this Ruby JIT age, we want less C extensions. In particular, less C to Ruby callbacks. So C extensions such as database binding is fine, like it's a Ruby to C call. But if you write a C extension that is designed for the use of Ruby and code into the Ruby methods, that could be problematic for Ruby performance, which is because this is a providing of the YJIT code with the layers application benchmark. And if you benchmark the cycles spent on the execution of the layers application benchmark, time spent on the YJIT code was only like 10%. So like even if you speed up the JIT code by like twice as faster, it shouldn't have like twice like 200% impact, because before the optimization, it's already just 10% of the whole execution time. This is because sometimes obviously spent on the DB queries, but we also have this interpreter-rated C function calls, and this mostly happens when you have C to Ruby code. So like whenever you enter a new Ruby frame from the C frame, you need to set up a lot of things for the interpreter to work, such as local variable environment, and also you need to save the entire stack in case Ruby frame raises an exception, and you still need to protect the C function frame to be alive. So because of that, if you have a C extension that calls back into Ruby, that makes the G code slower and also makes it harder to inline the whole thing and propagate constants and do the fold constants pass to optimize a lot of things by inlining the literal provided by somewhere to the callee to do the compile time optimization. So if you have C frame somewhere in the middle of the stack, then that makes it harder for JIT to optimize the Ruby code and also make it slower to just call into the Ruby frame. So we encourage people to not write the the C extension or Rust extension or Go extension if you need to call back into the Ruby code. If it's just a binding that just never call back to Ruby, that's fine. But other things that call the spend cycles in the C functions include the megamorphic call sites. So when a single call sites could dispatch into multiple targets, then if it's highly polymorphic, then we call it megamorphic. And in that case, we also have to sort of use a slower path, hash table-based dispatch. So it's also slower. So it's just showing that as a next example. But anyway, sometimes it's faster to rewrite C-based implementation into Ruby. So this is an example of a kernel top. It's just yield the block given to the tap method, and then it just evaluates a block and return it. So it's very simple if you implement it in Ruby. So it's like simple implementation, and it's also faster, so it's a win-win. But generally, when the C method calls into Ruby code such as a block, like yield, then you probably should write that in Ruby. So we keep doing this kind of rewrite into Ruby thing, and we also encourage you to not write C extensions if that calls into Ruby. So in conclusion, we are building ZJIT to unblock cross-instruction optimizations. By having the HIR, we believe that other optimizations that are enabled by other languages can be ported into Ruby and also be done in the Ruby language aware way. So in ZJIT, we are hoping to unblock many more optimizations that YJIT couldn't do. And also to add that we want more code to be written in Ruby in case, especially when the C extension calls back into Ruby, then we want that to be written in Ruby. So that's it. Thank you.